All right, so I just mentioned this in passing. Of course, what's most important, of course, is to know what does this look like for the first, like the first term in it is this, right? What's next? Next comes the gradient of f at the point that's given, that we're centering the series about, dotted with the difference vector. And then the second order piece, we can write a little bit nicer. What it really looks like is the vector x1 minus x bar 1, xn minus x bar n, times this matrix. The matrix looks like, let's see here, f11, f12, f1n, and we have f22, fnn down the diagonals. And then it's a symmetric matrix, so this is f12, f1n, and then times the difference vector again, x1 minus x bar 1, xn minus x bar n, and then higher order terms. I will stop talking about this abstract stuff here very soon. Just give me a second more and I'll shut up about it. But this is a real symmetric matrix. And one of the beautiful things we learn about in linear algebra is that if you have a real symmetric matrix, you can choose a system of coordinates in which all of the off-diagonal terms go away. And in that special system of coordinates, that formula, this piece, just drops down to like lambda 1, y1 squared, lambda 2, y2 squared, plus lambda n, yn squared. So that's what this quadratic piece, the Hessian, can always be rewritten as a sum of squares by choosing the proper system of coordinates. And that system of coordinates is known to exist by what's called the spectral theorem in linear algebra. If Math 321 goes well, I cover that towards the end. In Math 221, if I was to teach that, I would state the theorem, but I wouldn't prove it. But it's kind of an important theorem that if you have a real symmetric matrix, you can rewrite the formula for it to be sums of squares, which is really nice. Because sums of squares we can think about. All right. Got that out of my system. So what's next? What's our final? What's that? Yes, the closed set test is the final thought in this discussion of mins and maxes and so forth. So the closed set test, much like the closed interval test, has two parts to it, right? So a closed set is a set which has a well-defined boundary, and the boundary is part of the set. So we've got like an interior to the set, and we've got a boundary to the set. And oftentimes, we need to consider the boundary by a separate analysis than the interior of the set. The interior of the set, well, we can look for local mins and maxes. We actually don't even need to use the second derivative test in this problem, though. Just like if you think back to Calculus 1, did you need to check the first or second derivative test on your, if you found a critical point in the interior of your closed interval, did you need to check whether it was a local min or max there? You really didn't, because what you did was you found all the places where we had critical points in the interior of the closed interval. Then you checked the endpoints, and then you just pick winners and losers. For a continuous function on a closed interval, you will attain a min and max at a critical point or on the endpoints. So you don't even really need to go back and apply that second or first derivative test to analyze the critical points separately. I have a marker. Okay, so example. Suppose we're looking at f of xy, and let's do this 3 plus xy function again, right? But let's find the absolute extrema for f of xy on, let's see, let's make it interesting, like a snow cone. Whee! On this shape. All right, so here, I'll make this, keep it relatively simple. This point will be 1, 0. This point over here, minus 1, 0. And this is a half circle. Right? So I want to find out what's the absolute max and min of that function on that snow cone looking thing. Let me shade it. So the boundary here. There's two different approaches for dealing with the boundary, all right? The one approach is Lagrange multipliers. The other approach is just direct restriction of the function. Okay? I'll do both for this example. Lagrange multiplier is kind of a nice fit for the top half of it. So, okay, so, well, game plan, first of all. I'm sorry, I should tell you my game plan here. Here's our strategy. Game plane? No, something else. Number one, any of you guys see Dr. Van Voorhis on the news yesterday? So I got this email. Would you like to do an interview with local news about like March Madness statistics? Like what's the likelihood of filling out a complete whatever it's called? And so like I know Dr. Van Voorhis a little bit. Like I knew like, oh, this is so Dr. Van Voorhis. This is like right up his alley. So he's like within 15 minutes of the email being sent, he's like, I'll do it. It's like, yeah, that makes sense. So I don't know. Apparently, he gave an interview yesterday to local news about statistics of it. It's interesting. Okay, so, but anyway, let's get back to calculus. So number one is find local min-max within region. Let's call the region R. R. Oh, I noticed that you got to see the pirate captain joke again. Yes. I am a creature of habit. It's about this time of year I'll tell it, for whatever reason. I feel like my delivery last year was better, though. I don't know. Yeah. This year, too. And then find min-max on the boundary of R. And actually, the boundary of R, it's going to have two different pieces. There's going to be the top, and there's going to be the lines. The top half circle and the lines. Now, the top half circle, I'm going to use the method of Lagrange multipliers on that one, because it's just kind of easy to do that. Actually, we've already done number one. What's the answer to number one? What's the local min-max? 0, 0, right? That was problem one today. 0, 0 is a critical point. And so we can calculate, what is f of 0, 0 here? Yeah, f of 0, 0 is 3. Let's put that away. Save for later, all right? In fact, that's going to be step 3, is picking winners and losers. Right? Step 2 is where the fun is. So let's look at let's look at the top. So what's our constraint? It is x squared plus y squared equals to 1, right? We're on part of the unit circle. That's my g, my constraint function. But there's more, right? There's also that y is greater than or equal to 0. How do you impose an inequality in Lagrange multipliers? Not through direct calculation. You just have to like put it somewhere you see it and keep it in mind, right? Just if we find solutions to the Lagrange multiplier with y negative, irrelevant, right? Those are extraneous solutions. They're not even in the solution set. Let's see here. So the gradient of f should be equal to lambda times the gradient of g. This is the method of Lagrange multipliers. So, oh, you guys already calculated the gradient of f for me earlier today. It was yx. That's lambda times 2x, 2y. So that gives me that y is equal to 2 lambda x, and it also gives me that x is equal to 2 lambda y. Dividing these equations seems ever so nice to do, right? So dividing the equations gives me what? It gives me y over x equals to x over y. Therefore what? Yeah, or x squared equals to y squared, but yeah, sure. X squared equals to y squared, which then tells me that 2x squared equals to 1. Therefore, x squared is 1/2, which finally tells me that x is equal to plus or minus 1 over the square root of 2, right? And y is equal to plus or minus 1 over the square root of 2. So method of Lagrange multipliers reveals to me those special points on the top curve. Well, which of those points is on the top curve? Let's be specific. 2 of them, right? So consider 1 over root 2. Well, excuse me, let's say minus 1 over root 2, comma, 1 over root 2. That's on the unit circle, right? And 1 over root 2, 1 over root 2 are potential min-max points, right? Those are points where we might potentially reach an extremal value for the function. So what is the value of the function at those 2 points? Can you guys tell me? Let's see here. F of minus 1 over root 2, 1 over root 2, what's that equal to? We got ourselves 3 minus 1/2, right? So we get 5/2 on that point. And how about the other one with both the pluses? Yeah, 7 over 2. And yeah, decimal's not a bad idea here, 3.5 or 2.5. I mean, personally, I like decimals when I'm asking a question of comparison of numbers. That's one of the real strengths of decimal number representations, right? When you have decimal number representations in hand, it's easy to compare numbers and see which one's larger or smaller, so forth. If I've got, 13 364ths and I've got, 2 sevenths, which one's bigger, which one's smaller? I'd actually have to think about it, If I tell you 0.34 and 0.75, which is bigger and smaller, we all know 0.75, Anyway, so there's, again, save these for later. So at this point, we found critical points here, and then there's one up here, there's one up here, right? Now, how do we deal with those lines? How to deal with the lines? Let me give them names. Let's call this L sub r. Well, I mean 1 and 2. How about that? L1, L2. So we have to parameterize those. You're like, parameterize? I thought we were over that. No, parameterization will always be with us in here. Okay, so L1, let me draw the picture again, is like this, right? L2 is this guy. Sorry, my circle got squished. But the point is, what's this point down here? Like, oh, I don't think it's clear yet, did I? I'm sorry. In order to make this problem make sense, I need to tell you what that point is down here. What do you guys want to make it? I'll take 0, comma anything. What do you want? It's going to be negative. -1? All right, that seems especially lazy. I like it. Oh, yeah, I did that. Let me fix that. 2, 1. Yeah, that's the kind of thing that'll get you into trouble. So we just have to find parameterizations of these line segments. All right, so like L1. We would look at R1 of t equal to what? I mean, I'll start with 0 minus 1 plus t times what? Well, the end point, which is 1, 0, right? Minus the initial point, which was 0 minus 1. In other words, R1 of t, parameterization, should be what? It's, looks to me like t, comma, what we got here? 2t minus 1? For what? For what range of t? Yeah. This parameterizes what? It parameterizes L1, does it not? Let me check. What happens when you plug in 0? 0, negative 1. What happens when we plug in 1? 1, 1. Uh-oh. Oopsie daisies. I think I have a problem. That should not be a 2. I sold you guys a bill of goods. So, I don't know why we say that. What does that even mean, bill of goods? Anyway, here we go. T. So there's the parameterization of that line segment. So how do we figure out where there's a min or max for the function along that? Well, f restricted, right? F restricted to L1 is just a function of t. And so we would take f of t comma t minus 1. That would give me a function which tells me how the function behaves on that line segment, right? Sometimes I'll invent another letter. I'll call this g sub 1 or something, if you look at old solutions to problems I've written. But it's the restriction of f to that line. What is that equal to here? It's 3 plus xy, right, which is t times t minus 1. Actually, at this point, I'm going to give it a name. Let's call this g1 of t, because I get sick of writing that. So what do we have? We have a continuous function on a closed interval. How do you figure out where t is minimized and maximized? I mean, we're g1, so we got to find min max of g1 of t, which is, by the way, equal to t squared minus t plus 3 on the closed interval, 0 to 1. You're like, hooray, calculus 1, woohoo! Because we have found our way back to a closed interval problem, right? This is an extreme value problem from about 40% mark in calculus 1, maybe the halfway mark, somewhere in there. So how do we solve this? Pretty simple. What's dg1 dt? 2t minus 1. If that's equal to 0, what's that say? Looks to me like t is going to be a half. So that's my critical point in the interior of the closed interval. And what do I have to check? I got to check endpoints and the interior critical points on 0 to 1. And so what do you got? Got to check your g of 0, g1 of 0, your g1 of a half, and your g1 of 1. What's that give you? I'll reinterpret it. That's really just f of 0 minus 1. This is f of, looks like 1 half minus 1 half, I think. And finally f of 1, 0, I believe. What are those equal to? We got a 3. We got a 3 minus 1/4, right? And we got a 3 again. So of course this is 2.75. So going back to my original picture, we just picked up this point, and this point as other candidates for min-max for the function. All right? What do we have still to do? L2, right? So L2 parameterize R of t. And I'll do it like this time, right, going that way. So let's see here. Looks like I'll have a fine, 0 minus 1 plus t times what? Minus 1, 0, minus 0, minus 1. What is R2 of t? What's the parameterization of that line? This is just what? Minus 1, 1. So it looks like we've got a minus t, comma, minus 1 plus t. 0 less than or equal to t less than or equal to 1. Let's check it. Put t equal to 0, I get 0 minus 1. Good. Put t equals to 1, I get minus 1 comma 0. All right, so it does parameterize L2, as I claim. And then we got to look at f restricted to L2, right, which is we can look at as a function of time. That's going to be f of minus t comma t minus 1, which, by the way, is 3 minus t times t minus 1. Since x is equal to minus t and y is equal to t minus 1. So that is my G2, if you will. And we face yet another closed interval test. So here we go. We got G2 of t equal to minus t squared plus t plus 3 on the closed interval 0 to 1. We got to find min-maxes for this function. So I look for my interior point that could be, I think you know what's going to happen. It's going to be a lot like the last one. dg d2 G2 prime is minus 2t plus 1. Yet again, t equals to 1/2 ends up giving us a critical, right? G2 prime of 1/2 equals to 0. So we consider G2 of 0, we consider G2 of 1/2, we consider G2 of 1. G2 of 0 is f of 0 minus 1. We've actually already considered that in the last case. G2 of 1/2 is minus 1/2, fed to f. G of 1 is actually f of minus 1, 0. So the top and the bottom ones are 3, and the middle one is 3 plus 1/4, which of course would be 3.25. So we just picked up 3 more, well, it looked like 3 more points, right? But actually, when you look at it over here, we've got this, and we added that. But you know what? We already had that point in a previous study of L1. Oh man, if we ever do Calculus 3 online, I'm going to have to drop this topic. There is no earthly way I can do an example of this topic in 15 minutes or less. This has no place in online calculus. Oh, you don't? Okay. All right, it's good. I like your style. I'll subscribe to your newsletter. Let's see here. Actually, no one subscribes to newsletters anymore, right? I should say I subscribe to your channel, or something like that. How do you do Instagram? Like, what's that? Are you on Instagram? Can I follow you on Instagram? Is that how we do it? Or should I follow you on Twitter? I thought it'd be fun to start a Twitter account and just like document my grading. Like, just like a real-time document of grading. Like, oh, it's awful. You know, or, oh, wow, they actually figured this one out. I'm amazed. And stuff like that, you know? It'd be fun. I usually feel horrible about grading any test. Even you guys, like your first test was statistically an outlier in all of the first tests I've ever given in Calculus 3. And yet, in the midst of grading it, I'm just like, ah, how do they not know that? You know, but then when you actually add up the points at the end, that's when the true statistical picture of the class makes itself clear. And I never know what that is until I'm done grading. I just don't know. Point 3 is, you know, pick winners. You know, pick min-max amongst the candidates. So what do we got? We got a 3. We got a 3.5. We got a 2.5. Another 3. Another 3. A 2.75. So what's the absolute minimum and absolute maximum on R? Max is 3.5, I think, right? 3.5, which is equal to f of what? Of minus 1 over root 2, 1 over root 2. So it's attained at the point minus 1 over root 2, 1 over root 2. And the minimum for f of x on R is what? 2.5, yeah. 5, which is attained where? So it looks like the Lagrange multiplier method had its, it was all the fun stuff was in the Lagrange multiplier method. Everything else was just us making sure stuff didn't happen, right? So, yep. Oh no, yes, thank you. Plus plus. Minus plus, yes, thank you. Yes, I lost track of what I was looking at, so. Now, so you see how long it takes to go over one decent example here slowly, right? So I do usually ask one of these on the test, and this actually was more or less in the ballpark of what I tend to ask on a test for closed set tests. Something like this is a good question. I can't ask 3 of them. I can't even ask 2 of them, right? I can ask one of these. So I usually ask something kind of like this. In the notes, I would encourage you to study the other 3 examples I have there, right? I probably won't go over them in class. I think we need to move on at this point, unless there are further questions tomorrow. So thanks, guys.